connective constant of the honeycomb lattice is square root of 2 plus 2. Okay, so this result is due to Duminil-Copin and Smirnov, okay, in 2010. And it was conjectured by Nian-Huis in the 80s. And maybe a remark concerning this is that Nian-Huis is a physicist, and the way he conjectured this is based on computations that kind of don't make sense mathematically, and people still don't know how to make sense of them. So in this sense, this proof is not really based on this intuition, okay, even though probably formulating the conjecture was a first important step towards proving it. So, okay, maybe I should remember you what the honeycomb lattice is and what the connective constant of the lattice is. So, the honeycomb lattice, it's a graph. Okay. We'll call it H. Okay, so it's made of a set of vertices and of a set of edges. For this class, it will be important to say that, the set of vertices, it's a discrete subset of the plane. And the plane, we are going to say that the plane is really the set of complex numbers. So for all the class, okay, for all this lecture, I will let J denote the first cubic root of the unity, the first non-trivial cubic root of the unity. Okay, so what you have is that 1 plus j squared is equal to 0. And now the honeycomb lattice, it's just this picture, where the edges, okay, whereas this 0 here, it's just, the origin is just 0 of the complex plane. And the edges, they are of length 1. So what this means is that if you look at the set of vertices, this is the set of alpha j, alpha times 1, okay, plus beta j, alpha beta in Z, and I put the extra condition that alpha plus beta is not equal to 2 modulo 3. Okay, so if you look at, I have 0, then I have 1. This is 1, this is j. This is j squared, which is just minus 1 minus j. And minus 1 minus j, you can see that alpha plus beta is equal to minus 2, which is equal to 1 modulo 3. So it's not equal to 2 modulo 3. But this point here, okay, which is 1 plus j, it's not in there, okay, because of this condition. Okay, the set of points, okay, of the form alpha plus beta that are not in my graph, they are the center of the faces. Okay, and you see that basically, yeah, for each triangle of points, I'm just deleting one. So. Okay, so if I had all the points, basically I would have a triangular lattice, but I've deleted these things and now I have the hexagonal lattice. Okay, and the edges, they are the set of z prime included in V square, such that z minus z prime is equal to 1. Okay? And this gives you exactly this structure of the lattice. Okay. So now, if you remember, a self-avoiding walk of length and starting from O, okay, is a sequence of n plus 1 vertices n such that without, okay, such that for all I that I is a neighbor of z I minus 1, and for all I j, z I is different of zj. Okay, and if you remember what we did in one of the first lectures of this course, I say that if we call Cn the number of such self-avoiding walks, basically we have that limit when n goes to infinity of Cn to the 1 over n exists. And the idea to prove this was just to show that Cn was submultiplicative. This is equal to no. Okay, so what we want to prove today, okay, is that, so in fact today and tomorrow, we prove that mu is equal to square root of 2 plus 2. Any questions so far? Okay, so it's the first time that I'm teaching this result. So there might be some imprecision. So please don't hesitate. Don't refrain from asking questions. Okay, so maybe okay, this will come later, but maybe I can already tell you what this square root of 2 plus 2 is about. So what this is, okay, is actually 2 cosinus pi over 8. This number here. Okay, and we will see how it appears, but why is this equal to 2 cosinus pi over 8? Well, if you look at cos pi over 4, this is equal to square root of 2 over 2, but this is also equal to 2 cos square pi over 8 minus 1. Okay, I mean, it's equal to cos square minus sinus square of pi over 8, but we can always subtract cos square and add cos square. Okay, so what you get out of this is that 4 cos square pi over 8 is equal to, okay, so you just multiply this by 2. So you get square root of 2, and here you have minus 2. So you get this is equal to mu square. Okay, so this is where these mysterious numbers come from. Well, for right now it's not very informative, but you will see that it will come clearly in the proof why you get this number. Well, even though I mean there will still be a little bit of magic, but okay. So now another way to say to talk about mu. So mu it's the exponential rate of growth of the sequence Cn. But another way to describe it is to say that it's the inverse of the radius of convergence of the series Cn. Okay, so if you look at, okay, I will just modify the definition in a moment, but if you look at this, so x here is in R. If you look at this, so n larger than, well, it doesn't matter. Let's say that C0 is equal to 1 by definition. And you take here yes, Cn next to Cn. What you have is that Zn of x is equal to infinity if x is larger than mu, and that of x is finite if x is smaller than mu. Okay, so what we are going to do is really look at this quantity and show that it's infinite in some cases and finite in some others. We will not exactly be looking at this quantity because we will not look at exactly this kind of self-avoiding walk. So for practical reason, what we will do is we will start our walks at mid-edges. What is a mid-edge? It's just a point which is drawn in the middle of an edge. Okay, so basically what our walks will do is, okay, they will walk between points. So here. So here's this walk. I mean, a step of the walk could be this, then this, then this. No. This, this. Okay. This. Okay, and I will call this point A. So A will just be one half in the complex plane. So 1/2 0 in R2, but 1/2 in the complex plane. Okay, so just basically just the same thing instead, but instead of starting from the origin, you start from a mid-edge, okay? And at each step, what you're doing is, okay, you're just following a self-avoiding walk path, but you stop at So basically, I mean, like you see that at each step you have basically two choices. You can go here or there. Once you have made this first step, you can go here or there. Okay, and in fact, you will have less than two choices because sometimes you will see regions that you have already visited. Okay, so now if I called Cn to be the number of mid-edge self-avoiding walk with n steps. Okay, so like starting from A. Okay, what you can check is really that Cn is really related to Cn. So what we have is that, in fact, if you have a random walk on mid-edges, what you can do is just complete it by drawing these things. Okay, the two half edges that are missing, and you get a self-avoiding walk of length n plus 1 on vertices. So what's the idea is that, okay, here I had a walk starting from A, now I have a walk starting from 0. The only thing that I'm only counting 1/3 of the walk starting from 0 because I'm forcing the first step here. Okay, so I should have 3 Cn here to get Cn plus 1. And actually, when I'm doing this, I'm just counting mid-edge walks that are first going to the right. So I have to put a 2 here. Okay, so I mean, the exact relation is not important, but what is important is that going from Cn to C bar n doesn't change the growth rate, the radius of convergence of the series. Okay, so what we are really going to look at is this. Okay. So now what our ultimate goal is, okay, we'll define xc to be equal to 1 over square root of 2 plus 2. And we are going to prove that z of xc is equal to infinity, and that z of x is finite for x smaller than xc. Okay, and this will imply, okay, these two things imply that mu is equal to square root of is equal to xc minus 1. Okay. So okay, I will just use this. So the idea here is instead of counting just well, making a sum of paths and taking x to the length of the path here, to make something a bit more subtle, which will make the series assume complex values. Okay, and in our series we will have various parameters, and the objective will be to tune these parameters in order to have a function which in some sense is holomorphic, okay, in the discrete sense. So, okay, for this I'm going to use this notion. So I will consider omega, which is a domain, so a discrete domain. Okay, so what's a discrete domain? Okay, it will be a set of mid-edges. Okay, which is simply connected. So, okay, by simply connected, I just mean that it's connected and that its complement is also connected. And by connected, I mean the relation of neighborhood between mid edges is just this one, you know. This guy has 4 neighbors which are here, 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 and here. Okay, this is your neighbors if you can go from one to the other in one step. Okay. And I will want another thing. I will want that omega can be written as a union x might not be the best. Z, maybe Z is better. Okay. Y in V of Hx Hy. So I want, my thing will be a domain if it's okay, if it's simply connected, it's a simply connected set of mid-edges, and if it's a union of this kind of star. So if X is a vertex, you have 3 mid-edges that are adjacent to X. Okay? So this is one possibility. There are 2 kinds of vertices, some other that are, okay, this is Y and this is Hy. Okay, and the other possibility being this one. Okay, so if you want H0 would be these 3. And what I mean by this condition is that basically, okay, so here I'm giving you an example of domain. So I'm just taking all the mid-edges here. And all the mid-edges that, okay, so these colored stuff, they are half-edges. Sometimes they are as long as the edges I've drawn, but they are half-edges, okay? And I'm taking just these mid-edges and all the mid-edges corresponding to the white edges there. And you see that, okay, this is a domain, because it's really the union of the star corresponding to all these vertices. If I don't consider this guy, then I wouldn't have a domain, okay, because there is no way that I have this guy and this guy. Okay, this would still be a domain. If I don't have this, okay. So basically, yeah. So for instance, yeah, I can't have something like this, for instance. Okay. Well, okay. So this is a domain, and something like this. I take this mid-edge, this mid-edge, and this mid-edge. It wouldn't be a domain, because if I want to have these two, I would need to have this extra one here. Okay. So, and now if I have a self-avoiding walk gamma, I will just write gamma is included in omega. If so it's a bit improper because gamma is not a set, it's a sequence of mid-edges, but if all its elements are in omega. Okay, and I'm going to consider the following observable. So I will have lots of parameters. So given omega, okay, a vertex A in the boundary. So, okay. I mean, later on, A will be this vertex, but now let's say that A is any mid-edge on the boundary. Okay. So the boundary, there are just mid-edges that are adjacent to mid-edges that are not in omega. Okay. Just the usual notion of boundary. It's internal boundary, so it's a set in omega that are adjacent to mid-edges that are not in omega. So I have basically 4 parameters. And now I define a function f, which will be a function of a variable which will be a mid-edge. F of z is defined by the sum over all paths, over all self-avoiding paths gamma from A to Z, which are included in omega, of, well, x to the length of gamma. So length of gamma is just the number of edges that, well, the number of steps that gamma is making. So like the number of mid-edge we have in the sequence minus 1. And what I'm adding is a prefactor, which is exponential minus I sigma W gamma A so really, I mean, this is a function of z, a, omega, sigma, and x. But basically, these 4 parameters here, they are fixed. So I'm just considering it as a function of z. And I still have to define this winding number. So, except for the W, are the definitions clear? Are there any questions? Okay, so just to make things clear, I mean, here in omega, I have a finite number of vertices. Okay. So, in particular, this sum here is finite. So there is no problem in defining this as long as we have defined this. Okay, so what's the winding number? Well, it's how much it defines. It's really the angle by which the walk gamma turns between the 2 points A and D. So can I erase here? Okay, so if I start from here, basically, if I make a step like this, okay, then it means that the walk is turning by an angle pi/6, pi/3. Okay, and if I'm making a step like this, so I mean this is the starting point. Okay, so the trajectory gamma, it's oriented, it has a direction. Okay, and if I turn like this, okay, I'm just turning by minus pi/3. So I'm just following my walk and looking by how much I turn. Okay, and I call this a winding number. And the important thing is that the winding number, it's not a number, it's not an angle modulo 2 pi. It's really a real, it's a real number. Like if I'm turning twice, it's filmed, so I won't do it, but if I turn twice around myself, I'm just turning by 4 pi, not by 0. Okay, so for instance, if this walk ends up at Z here, and if I want to know what's the winding number of that walk, then, okay, well, you can just check, but it's, I'm just counting 1 when I'm turning in the positive sense and -1 when I'm turning in the negative sense. So I have 1, 0, -1, -2, -1. Okay, I guess I've made a mistake. Okay, so 1, 0, -1, -1, -2, -3, -2, -3. Okay, so -3 is -3 times pi/6, so it's pi. So I've made a turn of -pi, which kind of corresponds to. Okay, so for Z and D prime on omega, Z visited first. If I take 2 points in my gamma, 2 points that are visited by a path gamma, okay, I just defined this thing as the angle turned along gamma going from z to z prime. Okay, and now, okay, so I've just computed this angle by following all of the steps. And what's kind of nice is that actually you don't really have to do this to compute the winding number. And the reason is the following. So if you take, okay, let's forget that the self-avoiding walk cannot visit the sites that are already visited. Now we are just going to consider, instead of self-avoiding walk, a self-avoiding loop. So it's going to end up at the same site where it started. And basically, okay, so if I have a self-avoiding loop, and if I go from it, then basically I know that its winding number, okay, is either 2 pi or minus 2 pi. Okay, if I take the whole winding number of this path going from A to A, okay, it's not something that I'm going to prove, but because of this non-crossing restriction, basically, you cannot do. Okay, you have to do one round, okay, to get back to A, and you cannot do 2 rounds. Okay, and basically, if you start to go there, and you start to say, okay, I'm turning once, I'm turning twice, well, then I have to basically turn back to unwind before I go back to A. Okay, and so because of this, basically, for instance, if I have a walk starting from here and ending up there and that stays in omega, I know that the winding number is going to be 0. Okay? I mean, this is just because I can just extend it into a loop for which the winding number will be 2 pi. I know the winding number of this part is 2 pi, so this part has to have winding number 0. Okay, and for the same reason, if I look at the winding number of a walk that end up here or that end up there, it will have a fixed value. So here, okay, if I want to end up here, the winding number will have to be pi. If I want to end up here, it will have to be minus pi. If I want to end up here, will have to be 2 pi over 3. And if I want to end up here, it will be here and on the boundary, it will be minus 2 pi over 3. Okay, I mean, basically just the angle between these mid-edges. Okay? And this would not be true if I were not considering vertices on the boundary. If you have a vertex in the middle, really, the winding number can be as high as you want. Okay? If you have a very big omega, you just need to roll around. But the thing is that then to reach the boundary, you have to basically go out of the labyrinth that you have just created. Okay, so these are geometric considerations. I think if you were geometers, they would deserve a proof, but they are not, so we can just accept them as a fact. Okay. So is the definition of the winding number clear? Okay, so now I'm going to basically state probably the most important result of this lesson. Okay, so Okay, so V of omega is just a set of vertices, okay, that are in omega. Okay, I mean, omega is a set of mid-edges, so it's a set of vertex of my honeycomb lattice, which are surrounded by mid-edges that are in omega. So let's say that I have V in omega. So V, it is adjacent to 3 mid-edges. Okay, and what I claim is that proposition. So if sigma is equal to 5/8 and xc is equal to 1 over, well, x is equal to xc. Okay. Then what I have is that P minus V times F of P plus Q minus V times F of Q plus R minus V times F of R is equal to 0. Okay, so remember, I mean, F of P is a complex number, this is clear. But P and V, they are complex numbers as well. We have defined them as such. Okay, because I mean, this is the vertex of the honeycomb lattice. It's alpha plus beta j, where alpha and beta, the sum of alpha and beta is not equal to 2 modulo 3. And, well, this thing, it's the average between 2 consecutive vertices. Okay, so, okay. Why is this in any way related to holomorphicity, so discrete holomorphicity? So, if you want these mid-edges, okay, they are in correspondence with dual edges of your graph. Okay, because they are the midpoints of the dual edges. So, to A, basically, I can associate this dual edge. This dual edge. Okay, so basically, I mean, the 3 mid-edges surrounding V, they basically corresponds to the 3 dual edges that are going around V. So, now I can say the following. So, if this is true, I mean, this is just equivalent to say, so let me draw this triangle here. I have this dual triangle. So I have V star 1, V star 2, and V star 3. Okay, so what I have, what this is equivalent to, is it is to say that V star 1 minus V star 3 times yes, P plus V star 2 minus V star 1 F of Q plus V star. No, V star 2, yes, V star 1 minus V star 3, V star 3 minus minus v stars 2. R is equal to 0. Okay, why is this equivalent to that? What I've just done, I've just multiplied this quantity by, I guess, so it's P minus V. So it's P minus V. So I've just multiplied it by, I think it's I times 2 square root of 3. Let's see. Yeah, I think this is exactly this. So if this has length 1/2, and this thing has length square root of 3, okay, so just multiplying the length by 2 times square root of 3, and I'm just multiplying the argument by I. Okay, and now, okay, I could just, instead of defining f on the mid-edges, I could say that this is f of E1, this is f of E2, and this is f of E3. Okay, and now if you look at f as a function defined on dual edges, okay, this really corresponds to a contour integral. Okay, what you're really doing is integrating dz times f, okay, which is just constant on the edges, and you're saying that the contour integral is 0. Okay, and complex valued functions that have contour integrals equal to 0, they are holomorphic functions. Okay, so here it's not holomorphic because the function is not continuous, okay, and it's not defined on the whole plane. But the idea is that if a scaling limit of this exists, then it would be a continuous function. Okay, so I mean, people don't know how to know this, but basically, okay, this was believed at least to be kind of the first step to unlock basically proof concerning scaling limit of the self-avoiding loop. Okay, and basically for the moment, people have just used this identity to get this okay, the value of the connective constant, but okay, maybe there is more in front. Okay. And maybe something more about this thing about integrating on contour. What we are going to do next is that basically, I mean, if this is true for a small triangle, basically, you know that, I mean, you can put the contour side by side, okay, and the edges, if you put, taking a contour, I'm integrating against the triangle, and then I'm integrating against the triangle next. And against this triangle, and I put lots of triangles together. What will happen is that I will only see an integral on the boundary of my whole stacking of triangles. Because when I stack two triangles together, basically because I'm all running around them in the trigonometric sense, basically this integral here and this integral here, they will cancel. Okay, so what we are going to use ultimately is that the integral of f around this big, around the boundary of omega, basically is equal to 0. Okay, so let's see how the proof of this works and where the specific values for sigma and x enters into the game. Any questions so far? Okay, so so if you look at this, this is just a sum over path. Okay, so the rule of the game here is basically to group terms together so that they cancel out. Okay, and to group them together, I mean, you have to get walks that are really much alike. So let's try to see how this is possible, what kind of terms, what kind of walks can we group together, and okay, see where it leads us. So, okay, so we are looking at walks that end up either at P, Q, or R. Okay, so P, Q, or R. And so there are three possibilities, basically. Either you will visit one of these three mid-edges, so basically you will stop when you visit them. Or you will visit two of them, or you will visit three of them. If you visit one of them, well, okay, your walk will kind of look like this. So one mid-edge. PQR visited. So if I visit one mid-edge, basically, my walk will look like this. Okay, so I stop there, and I basically stop when I hit this this set of three vertices. Now, if I visit two mid-edges, basically, what happens is that immediately after I visit one, I have to visit the second one, because I can't backtrack, so the only two adjacent mid-edges that are allowed to visit are these two ones. So, okay, so basically, this is kind of a good news. What we will want to do is, I mean, this walk is very much like this one. Okay, just as an extra step. So basically, the walk that visit two mid-edges, we can always couple them with walks that visit one mid-edge of the three. And actually, these things go by triplet, okay? Because if I have a walk that visits one mid-edge, then I can extend it in two ways to visit two mid-edges. Okay, and then I have the third option, which is when I visit three mid-edges. So, I mean, in my drawings, I just visit P first because it's more convenient. And I will also, this is also the way I will do this in the group. Things would be exactly the same. Would visit another. I mean, it's just a matter of labeling. Okay. So now, if I visit two mid-edge, three mid-edges, basically it's that I visit first two, and then I have to end at the last one. Okay, and basically now I can. I can say, well, if I have a walk that visits first P, then Q, then R, then Q, then I can couple it with a walk that visit first P, then Q, then R. Okay, I just take the same sequence of vertices, but I just visit it in the opposite order. Okay, so my idea, not my idea, the idea, the idea of these authors, also Duminil, Copain, and Smirnov, is to say, okay, now I can group together in my sum. I can group together walks in the following way. So if I can group a walk that visits first P with a walk that visits P and R and P and Q, okay, and the same if a walk visits first Q, I will group it. And the walks that visit P, Q, and R in this order, I can always group them 2 by 2 in this fashion. Okay, and in this way, I have all the terms of the sum, okay, and I'm not counting these things twice. So what I have to show, if I want to show that this is true, is that basically the contribution of a pair like this is equal to 0, and the contribution of a triplet like this is equal to 0. So is the reasoning here? Okay, so let's go to this case first. Okay, and to see what happens. Okay, so clearly I have to take. Okay, let me write. Let me write the function of f here. This way. Is equal to the sum of gamma A z of exponential minus I sigma W gamma A z x to the L of lambda. Okay. Okay, and this, I will just assume that all the gammas we are considering, they stay within omega, so maybe it will be easier not to write things in the equations, just to allow me to write bigger letters. Okay. So, okay, let's see if I'm able to do this without any mistakes. So, okay. So let me define yes. Well, C maybe it's not the best definition. Okay, F of gamma it's equal to Z minus V exponential minus I sigma W gamma Z X C L gamma Z is okay. Okay, where is Z? Is Z endpoint of gamma. Okay, so this f gamma v, it's just the contribution, okay, of gamma to this sum. Okay, so it's the contribution of gamma in, sorry. It's the contribution of gamma to this sum. Okay, but because I have this prefactor here. Okay, so what I want to show here is that f of gamma 1 is equal to f to the minus gamma 2, minus f2 of gamma 2. Okay, to show that the contribution is cancel out. Okay, so let's try to do it. So let's write what's okay. So if you look at L of gamma 1, it's equal to L of gamma 2. So these factors, they will be the same. You don't have to care about them. Now you have to look at the winding numbers. Okay, maybe another thing I can say first is that let's see. R minus V, it's equal to J times Q minus V. Okay, so you get this factor J between them. Okay. Now the winding numbers. So if you look at the winding number of gamma 1 between A and R, this is equal to the winding number of gamma 1 between A and P plus the winding number of gamma 1 between gamma 1 ends up at Q, sorry. Between P and Q. And, well, this thing is, I'm going here, this thing now is going there, and I've turned in this direction. So I've turned in the negative sense, okay, by an amount which is basically 4 pi over 3. Okay, so this is minus. Minus 4 pi over 3. Do you agree? I mean, yeah, it's very close to being a loop here, okay? So this, I mean, the winding number has to be fixed. It's the same for every loop that we do this. And yes, I mean, basically from here, I just need to turn twice to get the same orientation. Okay, so pi over 6, pi over 6. So what I'm pi over 3, pi over 3. So what I'm missing to be doing the full minus 2 pi loop. Okay, I'm running in the inverse trigonometric sense. Here is this angle 2 pi over 3. Okay, and for the same reason, W gamma 2 AR, it's equal to W gamma 2 AP plus 4 pi over 3. Okay, the reason is that to go from P to R, now you are rotating in the positive sense and by 4 pi over 3. Okay, so now what do we get? We get that f gamma 2 Okay, it's equal to, okay, so we start with R minus V, so R minus V is J times Q minus V. Okay, then you get xc to the L of gamma 2, but this is the same as xc to the L of gamma 1. And then I get, well, exponential minus sigma W this is important. Okay, so these two things, I mean, the two first part of the path, they are the same, so they are the same winding numbers. The second part, they don't give the same contribution, but you know exactly what the contribution is. So therefore, you know that the difference between the two winding numbers is 8 pi over 3. Okay, so A Q A R, sorry. Okay, but this is W gamma 1 A Q plus A pi. Okay, so what I get is that f of gamma 2 is equal to f of gamma 1. Okay. But the difference is that I have a factor j, and I have a factor exponential minus I sigma 8 pi over 3. Okay, now sigma is equal to 5 over 8 by choice. So this is just exponential minus 5 over 3 pi. And plus 2 pi over 3. So this is okay, because of the j. So this is just exponential minus I pi. This is minus 1. Okay, so here basically you can check that okay, we have not used the value of x here, but we have used the value of sigma. Okay, if the value of sigma was not equal to this, then we would be in trouble. Okay, and yes, I mean, you could take sigma much bigger, but basically, I mean, if you multiply sigma by a multiple of 6, then you don't really change the value of f. So you change the winding numbers, but you change sigma times the winding number by a multiple of 2 pi, so you don't change this subset. Okay, so basically modulo this thing. This is a unique value of sigma that makes things work. Okay, so basically this pairing between paths kind of forces a unique value of sigma for this to be valid. And this second thing here will force the value of x. Okay, so this is the reason why this result is valid only for this value of sigma and this value of x. So far, so good? Okay, so I think I better, okay, maybe I can erase this, but I have to keep this. I will keep this as well. See.
Could you repeat again why is measuring? What is the F measuring? So what is the idea behind constructing that function?
The big F? The small f. Oh, the small f is just the contribution of the path gamma to this sum. Okay, so this f, okay, it's just this thing, okay, multiplied by the prefactor here. And this is R minus V, sorry. Okay, so I know that, yeah, so the idea is that, the right-hand side, the left-hand side of my identity here, it's equal to the sum over some gammas. So the sum of gammas from A to P, Q, R of F of gamma. Okay, and what I want to say is that, okay, I want to show that this thing is equal to 0. So I'm going to group terms together. I have grouped this gamma 1, gamma 2 together. I'm saying, okay, the sum of these two is equal to 0. Now I'm going to say the sum of these three is equal to 0. And this is just a bunch of group of distinct, disjoint group of 2s and 3s. So the sum of everything is equal to 0. Okay. So, and in this thing, basically, what was different between gamma 1 and gamma 2 was the argument. The modulus was the same. And the argument was not the same for two reasons. Basically, because this prefactor here gave a difference of a factor j, and the winding numbers also was different. So it gave a difference of sigma times this 8 pi over 3. Okay, and then you just tune sigma for these two differences to sum to pi so that you would get things to cancel out. Okay. What I'm proving exactly is that if I have two paths, okay, so if I have gamma 1, which is A, P, R, Q, and gamma 2 is equal to A, P, Q, R. And what's really important is that here, this sequence and this sequence are the same. And here, this sequence and that sequence, they are the same, except that this one is read in the reverse order. Okay? So if these two paths have exactly this relation between them, okay, then they satisfy what I've said. Actually, I don't actually need this. What I really use in the reasoning is basically that here that the total length is the same, that the winding numbers between this and this is the same, and that's pretty much it, because here the winding number was forced. But what's important in the say that is that this really gives me a pairing. Like there is really there is a bijective, there is a transformation that from this gives me this, okay? And it's a one-to-one bijection between paths that first visit R and then Q, and path that first visit Q and then R after visiting. Okay, so the fact that the transformation is bijective guarantees that you're making this pairing in a way that all your pairs will be disjoint, which is important when you're doing this. Any more doubts? Okay, so from now, now we are going, this way of grouping paths by 3, it's kind of much easier. Okay, so in this new case, what I will have is that A is just a given sequence that ends up to P, and gamma 2 will just be exactly the same sequence. Okay, it will be gamma 1 Q, no, it will be gamma 1 R, okay, and gamma 3. Well, okay, let this one be gamma 2 and this one be gamma 3. Okay, so I'm just taking exactly the same sequence, and I'm taking one more vertex, one more mid-edge. Okay, just one more step. Okay, and gamma 1 is just a sequence that ends up at P without visiting Q and R. So what I want to say is that I can basically group trajectories that visit one vertex and trajectories that visit one mid-edge and trajectories that visit two mid-edge in this form of triplets. Okay? So what I want to say now is that f of gamma 1 plus f of gamma 2 plus f of gamma 3 is equal to 0. And what I want to really do is to say, okay, f of gamma 2 and f of gamma 3, it's basically f of gamma 1 times something. And I want to say that 1 plus something plus another something is equal to 0. Okay, so the length of gamma 2 is equal to the length of gamma 3. It is equal to 0. This is easy. And now the winding number of gamma 2, well, between A and Q, it's equal to the winding number of gamma 1 between A and P minus pi over 3. Correct me if I'm wrong. This is fine. And the winding number of gamma 3 between A and R is equal to the winding number of gamma 1 between A and R between A and P plus pi over 3. Okay, so now if I look at F gamma 2 and F gamma 3, I will have basically 3 differences. So, oh, sorry, no, this is, okay, I don't know why I've written that. This is L of gamma 1 plus 1. Okay, so I have 3 differences, basically because the length is the length of gamma 1 plus 1. I will have a factor x, which and then So the modulus will be changed by this, and then the argument will be changed by two sources. So first, the winding number is not the same. So I will have this sigma plus or minus 1 pi over 3. And I will have this factor either j or j square coming from there. OK. So if I look at f of gamma 2, OK, this is equal to, so, OK. First, I have q minus v. But I know that this is just j times p minus v. Okay, it's p minus v that I have rotated by 2 pi over 3. Then I have xc. Okay, to the xc to the L of gamma 2. Okay, but this is just L of gamma 1 plus 1. And then I have exponential I sigma times the winding of gamma 2 from A to Q. But this is just, and there is a minus here. And this is just the winding of gamma 1 from A to P minus pi over 3. Okay, so from this, I get that f of gamma 2 is equal to j times xc times exponential. So here I have a minus, but here I have also a minus. So I get I sigma pi over 3. Okay, and in the same manner, f of gamma 3. So here I would get j square. On x, I get exactly the same thing. And on the winding, I get plus instead of minus. So j square xc exponential I sigma minus I sigma pi over 3. Okay, and here I get f of gamma 1. Okay, so to conclude, I just have to show that 1 plus this is equal to 0. Okay, so you have to show that this plus this is equal to minus 1. Okay, so I have xc times exponential I. So okay, so I have exponential I 2 pi over 3. And now this is plus, and this, okay, sigma is 5 over, it's 5 over 8, I guess, so 5 over 8. Okay. So I 5p over 24. Okay, and this is where okay, so here you just get the complex conjugate. And now we have to compute exactly this. So what is 2 over 3 plus 5 over 24? Normally, there should be some simplification. So I get 21 over 24. Yes. So this is 7 over 8. Okay. So from this, you get xc times 2 times cos 7 pi over 8. Okay, which is just minus 2 xc cos pi over 8. Okay, which is equal to minus 1. Okay, because 2 cos pi over 8, it's mu, and xc is 1 over mu. Okay, so this is basically where the value of x comes, and this is the only place in the computation you will get. Okay, so yes, I think we are almost, well, we are basically done for today. And now I will take 15 minutes basically to announce what we are going to do next time, and basically to explain why I drew this picture. Okay, so is the proof of this proposition clear? Okay, you want to show that this f, which kind of looks like a generating function for gamma restricted to a domain, okay, but with this twist that you put winding numbers in front, you want to show that this satisfies some kind of local identity which is similar to holomorphicity. And in order to prove this, what you show is that grouping paths in a suitable manner, you show that this contribution of the group of paths is equal to 0. Okay, so now what we are going to do is, so this is a local identity. From this we are going to deduce a kind of a global identity. What we have is that if A belongs to the boundary of the domain, and if for B in delta omega, VB denotes the vertex in omega adjacent to the mid-edge P. So if you have a mid-edge which is in the boundary of omega, it's only adjacent to one vertex. So I just call it VB. Then what we have is that I have a 2 in my note, but I think it's not there. So let's see. The sum over B. No, I have a 2. The sum over B in the boundary of omega minus A of FB times B minus VB. It is equal to 1. Okay, so why is this true? So, in order to prove this, what you really only need to do is to just sum this identity over all these that are in omega. Okay, so okay, and now look at if you look at a vertex in omega, basically it will appear in this identity and it will appear in this identity. But in what case it will get this minus v? Well, it will get this minus. Okay, this is let's call it z. Okay, and this is v1. This is v2. So in one case, you will get fz times v1 minus z, and in the other case, you will get fz times v2 minus z. v1 minus z and v2 minus z are opposed, so they will cancel out. So the only terms that don't cancel out are for vertices that are mid-edges that are adjacent just to one vertex. And these are exactly the mid-edges on the boundary. Okay, so the contribution of internal mid-edges cancel out. Oh, and then you will discover that I have omitted something in the proof, but this doesn't matter very much. So what we get is that sum over B in d gamma of B minus VB FB is equal to 1. And, well, now comes the question, yes, but what's FA? And, yes. So. And now, by definition, FA is equal to 1. Okay, FA, I mean, this set is equal just, the only gamma is the gamma of length 0. So it has length 0 and it has also winding number 0. So f of a is equal to 1. And you can see that, I mean, with this definition of the length and the winding number for paths of length 0, the proof I had before is still valid. Okay. The thing was just, I mean, this coupling between gamma 1, gamma 2, and gamma 3, and it's still valid if gamma 1 is a path of length 0. And here, okay, this thing is valid. Yes, okay. Maybe it's better to write it like this. So this is equal to A. Yes, okay. Maybe you want something like this. VB minus B, and here you will get A minus VA. No. B minus VB, this is good, and then you get A minus A. Okay, so this is equal to 0, and in order to get this, you just shift the term of A. Okay, so yes, I think I can conclude in a short amount of time. So what we will do next time is start from this identity, but in a specific domain. Okay, so my A will be just here, okay? And I will consider basically a domain which is symmetric around A, okay? So I just have L edges, L min edges on each side of A. Okay, here L is equal to 3. And then I will make it kind of a trapeze shape. So here this will be T. So here in my T4. And our starting point will be this identity here. So in this specific case, okay, VA minus A, it's equal to 1/2, so it's equal to 1. Okay. If you multiply it by 2, and you will want to multiply everything by 2, this thing has modulus 1/2, you get 1. Okay, so what you get is that this sum is equal to a positive constant. Okay, very good. Now, the other important thing in that in this sum, basically, you can get rid of the winding numbers here. Okay, so what I'm saying is that in the sum you have here, you will be able to get rid of that. And the reason is the following, is that basically, if you go from, okay, so what we will do is separate things on whether they are going from A to the same side as A, they are going to A to the other side, or they are going to A and ending up in laterals. Okay? If they go from A to the other side, well, the winding number is 0. So you don't have this term. And this B minus VB, it's 1/2. Okay, so I mean, in this sum, okay, apart from this 1/2, you just get exactly the sum of paths. Here, you have to couple the path 2 by 2. Okay, so basically, you have paths going up here and paths going up there. Okay, and if you look at 2 of them, they have just contributions that are the conjugate one to another. Okay, so this is how the arguments will cancel out. You will get a cosine. Okay, and the important thing is that here, okay, the argument will be pi. You multiply pi by 5/8. 5/8 is larger than 1/2. So you get something which is larger than pi/2. So you get a negative cosine, but then you multiply it by minus 1/2 here. So you get something which is positive. So again, you get the sum of x to the L to the gamma by something which is positive. And you're happy. Okay, and the same thing happens kind of miraculously from, okay. I mean, it's also that this shape has been specifically defined for this purpose. But, okay, things going out there, the winding number is 2 pi/3, and they have a contribution which is the complex conjugate of path going out there. So you just have to worry about the real part. And basically, again, in the angle, you have these 2 pi over 3 that plays a role, so these sigmas that times 2 pi over 3. And you also have this fact that here you're multiplying by j. And it turned out that altogether, this gives you a positive contribution. So what you have is that, yeah, basically, the sum of the number of paths, I mean, apart from 3 factors, you have that the sum of xc times the x times the length for all these paths is equal to 1. Okay, and from this we can work a little bit. So, I mean, there is still some work to be done, but this will be our starting point. So what I will do next time is start from this identity, I mean, state this from this kind of trapezoid shape, and justify that you can cancel the winding numbers, and okay, see how from there you can get the value of mu. Okay. Any questions? Okay, so I think hopefully we will finish this tomorrow, and I think maybe on Friday we will start to introduce the Ising model, which will be basically the program for the modes of Fredwell. And I have to work on the list of exercises too. Thank you.